Hi, I'm Eric Wedewald and I'm with the Data Lab at Northeastern University. And this is joint work with Rundong Li, who's now at Google, and with Wolfgang Gadebauer. We're interested in distributed band joint computation. So let's dive right in and look at some examples for band joints. In this paper, we only consider joints between two relations, but we're interested in different dimensionalities. The first example is a join on the single day attribute. So this is a one-dimensional band join. The second example for the bird and weather data joins on latitude, longitude, and time. So this is a three-dimensional band join. Let's build up a little more intuition about band joints by looking at the one-dimensional problem. Here we see for epsilon equal to 0 the join matrix between S and T, where we have the day values of S on the rows and the day values of T on the columns. And you can see that only equal values can join, meaning that this is just a classic equijoin. When we increase epsilon, the band becomes wider. So now, for instance, a 2 in S can join with 1, 2, and 3 in T. And if we keep on doing that, at some point, this join becomes a full Cartesian product where every S tuple joins with every T tuple. This means overall, band joints are generalizing the entire spectrum from equijoin all the way to Cartesian product. Now, what are we optimizing for in a distributed system? The classic optimization goal is simply to improve load balance, meaning we want to minimize the maximum worker load, which is determined by the amount of input and output assigned to the most loaded worker. In addition to that, we are also interested in total communication cost, because data has to be shuffled and moved between the machines, and this cost is determined by the total amount of input, which includes the original input and any duplicates that are generated by the partitioning scheme. Overall, we are minimizing the weighted sum of the input and output assigned to the most loaded worker and the total amount of input that is communicated through the network. This is a very widely applicable model. For instance, it applies to any MapReduce and Spark computation where data is shuffled between machines. It also applies when data is hosted on a separate cloud storage like S3 and has to be moved to the compute cluster. For superfast networks, we can simply set the weight on the I-term to 0. And we can similarly use this also to optimize the partitioning of an array in an array DBMS. Now, why is distributed band joint computation difficult? Let's look at a simple example where we have integer numbers between 1 and 10, and the little boxes in the picture identify the tuples that are in S and in T. And epsilon here is equal to 1. Assume we want to now distribute the work over two machines. What can we do? Well, ideally here in this case, we simply cut the data in half, send one half to worker 1, the other half to worker 2. And ideally we get this nicely balanced load where half of the S and T tuples are on each machine, and also half of the output is produced by each of the two workers. Now, can you see a problem here? So if you look closely, you can see that some output tuples are actually missing here. And these are tuples where one of the join partners is on the other side of the partition boundary. We can fix that by simply duplicating tuples. In this case, we copied the 5 and the 6 of T across the partition boundary. And now we get a correct output, and we still have a nice distributed computation and only a small input duplication overhead. Can we actually do better than that? All right, so if you look carefully, it turns out if we split at the right places here between 2 and 3 and between 8 and 9, we still can get a perfectly balanced load, but now actually with a lower per worker load, because we do not have to duplicate any input tuples. The big challenge here is how can we find these good split points? And what we propose is to follow essentially the geometry of the original join attribute space and to find sparse regions by carefully splitting where we have few tuples to duplicate across the partition boundary. This is inspired by decision trees. So let me show you with an example how this works for a two-dimensional band join on attributes A1 and A2. Initially, the space is not partitioned and the split tree is empty. Like in a decision tree, we're now looking for the best possible horizontal or vertical split. Let's assume in this case it's on attribute A2, a horizontal split on value A. Then we keep on recursively partitioning, in this case, leaf number 1 into 1, 1 and 1, 2, this time splitting on attribute A1. You will realize that as we keep splitting and these partitions become smaller, at some point they will approach bandwidth. And when that happens, we switch internally to a different partitioning scheme for these small partitions. This partitioning is inspired by the one-bucket algorithm, which was shown to be optimal for cross-product computation in a distributed system. And notice that this is not the same as regular grid partitioning because tuples are randomized across these different partitions. Afterward, the algorithm may return and split 1.2 again. So now it has 3 internal partitions. And let's look at one more step. Again, an internal partitioning step and leaf number 1.2. As a result, we now have a tree whose leaves are either regular partitions or such small partitions like 1.2 that have a further internal partitioning. To make this work, we had to overcome several technical challenges. The first one is, given a potentially high-dimensional space and the hierarchical partitioning of that space, which of the S and the T tuples have to be copied across which of the partition boundaries? It turns out that we can solve that elegantly by following the split hierarchy of the tree, and this also allows us to treat S and T symmetrically, meaning at some split points we can copy S tuples and at others we can copy T tuples. The next big decision is about how to choose the best split point. In particular, we have to decide, given that some splits are better in terms of load balance, others are better in terms of input duplication, which of them should we prefer in the end? We propose to use the ratio of maximum worker load improvement versus the number of additional copies of input produced by that split. Unfortunately, the numerator, max worker load improvement, is difficult to estimate, and so we're proposing here load variance reduction as a proxy, and this is based on a mathematical model that uses random assignment of load pieces to workers. Having settled on a split scoring measure, we now have to determine when to stop splitting. For that, we manage all the leaves of the split tree in a priority queue, splitting the one at the top first, and we stop the split process as soon as the cost of splitting outweighs the benefit. To determine that point, we propose 2 conditions, a practical and a theoretical condition. The practical condition uses a distributed running time model, and that model simply predicts at what time further splitting does not improve running time anymore. The second one is surprising in the sense that it does not need a distributed running time model, but only essentially a standard cost model as used by Database Optimizer. This model finds the optimal point in terms of the overhead of input size and maximum worker load compared to the lower bound. Now let's take a look how well the method does in practice. We compare across a wide variety of datasets, bandwidth, and cluster sizes, and we compare against the state of the art. The first competitor is grid epsilon, which partitions the attribute space into a regular grid, where grid size in each dimension is the bandwidth in that dimension. On the left, you see a graph that shows on the x-axis the overhead in terms of input size against the lower bound. Similarly, on the y-axis, we see the overhead of max worker load against the lower bound. Notice that both axes are log scale. What we see here is that grid epsilon is pretty much all over the place, and in some cases, it is actually 10, 100, or even 1,000 times worse than the lower bound. The next competitor is one bucket. It is a theta join algorithm that supports band joins, and like grid epsilon, it has a very low optimization cost. It does somewhat better, but you can see that it can still be about 10 times worse than the lower bound. The state-of-the-art competitor for band joins is CSIO. As you can see on the left, it is a lot better than one bucket in grid epsilon, in some cases only 10% worse than the lower bound, in other cases about twice as bad. The main downside of CSIO is the high optimization cost. CSIO uses rectangle tiling, which is even more expensive in terms of computation cost than the join itself. This means that CSIO requires careful tuning to not exceed the join time. In our experiments, it turned out that for the best configuration, CSIO's running time for optimization rivaled the actual join time afterwards. So where join time was between 5 minutes and 1 hour, CSIO needed about 20 seconds to 25 minutes in some cases to find the partitionings. The clear winner here is our rect part algorithm. Looking at the left, you can see that it is never more than 10% worse than the lower bound. And it finds these really good partitions within about 3 seconds running time. And given that a join takes about 5 minutes to 1 hour to compute, 3 seconds for optimization is fairly negligible in this case. Why did RegPart do so well in the experiments? We believe the secret to success is that it splits in the original attribute space defined by the join attributes. And in this space, it is looking directly for sparse regions where it can partition without a lot of input duplication. And this is very different from algorithms like CSIO, which are partitioning the join matrix, which is always the two-dimensional matrix between the S tuples and the T tuples. The downside of working directly in the join attribute space is that now we have a potentially high-dimensional partitioning problem. To address this, we propose recursive partitioning, which in our experiments found solutions with low maximum worker load that was close to the lower bound. It had negligible input duplication, and the algorithm found those partitionings really quickly. You can find other analytical results in our paper. For instance, we study for grid partitioning under which conditions it performs well and when it will perform poorly. Here it was particularly surprising to see that under certain conditions, as data becomes larger, grid partitioning will behave better. Similarly, we explore join matrix covering approaches like CSIO and explore how to organize the S and the T tuples in the join matrix for best performance. For future work, we would like to show analytically that RegPart has to be close to the lower bound. Thank you very much for your attention, and I'm happy to take any questions.